Physics Bites,
a science podcast in English by the students of Notre Dame d'Instruction.
So hello again and welcome to a new episode of Physics Bites, the English language physics podcast from the students of Notre Dame d'Instruction here in Paris. We have two new students who are going to be talking to us about time travel. Is it possible? Is it impossible? The paradoxes and all the fun, juicy science fiction details of it. I also have a new co-host today. Hello, co-host.
Morning.
Hello. So this is Antoine, which you've heard already. You did the podcast on
everything about gravitation, and we did
cosmology,
right. Yeah, more generally.
Right, relativity applied to the universe. And so the two new students. Hello, new students. Do you guys want to present yourselves?
Hello, I'm Zainab.
And hello, I'm Rose.
So Zainab, you heard last time because she was filling in for Lola on the presentation about gravitation. And today is her topic, along with Rose. They're going to talk to us about time travel. So how about we start with you guys giving us a brief summary of the stuff you talked about during your presentation?
Yes.
So Rose is going to start.
Yeah. So we started with a small introduction about the whole time travel idea, and then we tried to present the different ways that could make this trip possible. So Zainab made a quick reminder about the Einstein theory of general relativity.
Right, because you guys used a lot of relativity to explain the possibilities of time travel, but not only relativity.
Yeah, and then she introduced other theories. Like cosmic strings and closed time-like curves.
Right. Which was going into much more very advanced bits of physics there.
So maybe you can talk about it.
So
Zainab, you want to begin then for us, okay?
I'll give you a quick summary, a quick explanation about what cosmic strings are. So cosmic strings are like defect in the fabric of space, and they like have a big gravitational pull, which allow you, if you can like get into this gravitational pull, to go faster than light and go back in time, because when light is when you are at the speed of light, time like actwardly, and it goes backward and not forward.
Right, and that's a consequence of what we call special relativity, which is even relativity before gravitation, where we sort of get the idea from Einstein that the speed of light is a limit, and if we see somebody going close to the speed of light, to us, time seems like it's slowing down, and when they get close to the speed of light, the closer they get, the slower it comes. And when they're at the speed of light, which is technically impossible, then time technically stops. So if they're going faster, it goes naturally that time would be flowing backwards. Now, that's the theory behind it. The question is that actually possible, right? So can you tell us, you said that cosmic strings are a defect in the fabric of space-time. What does that mean?
It actually, when the Big Bang took place, there was like the space was even everywhere.
Right. Do you remember what the word for that is? What this description of space, which is even everywhere?
No.
They call it isotropic space.
Isotropic space.
Right.
And then after a few seconds, the temperature of the universe dropped, and this drop in temperature made like it was like in an ice cube. You know, your ice cube, it doesn't it doesn't have a transparent it's always have little
so what you're talking about is when water goes from a liquid state to a solid state, what we call a phase transition. And so you're saying that the idea is that the universe after the Big Bang was very, very hot, and as it cooled down, whatever matter was in the universe also
had a phase transition.
Right, had a phase transition. And the way that phase transition for water from liquid to solid is never perfect, because if it was perfect, it would be perfectly transparent. So there's defects in the way it solidifies and crystallizes. You're saying that the same thing we think may have happened.
Yes, it may have happened, and it like there is the atoms and the molecules that were composed like at the time when they shifted their temperature. They had like two levels of energy that they can take.
Okay.
And it's actually when it started from a place, it's like it took like they took a certain amount of energy, and another place they took another. So when the two bubbles that started to be met, there was like uneven place where the energy wasn't the same, and so that is.
So this is the theory behind what cosmic strings are. I guess there's a couple of questions we can ask already about that. What do you think, Antoine? What are?
I believe I've seen one about the fact that do we really believe in them, or do we have some proof that could prove that they're real, or is it just?
Have we observed any cosmic strings?
No.
Thus far,
we never observed the cosmic strings. It's just a theory, but it's likely to be true.
Okay, so if I'm not mistaken, I think the theory dates back to the 1970s. I think it was Tom Kibble who came up with the idea. We have never observed it. Do you know what would we be looking for if we wanted to observe a cosmic string? What would it look like?
I think.
What are do you have some physical characteristics of a cosmic string?
It's like a shift in the gravitational pull in the universe. For example, when a cosmic strings move, like there is a little move in it, it will create a loop that will move through space.
Okay.
And this.
Why is that? Why does it have this effect on space and time?
It's because it's very condensed.
Right, it's very heavy, right?
Yeah,
even a small little string, which might be a couple of meters long, would have more mass than Mars or even the sun, depending on what it is. But it's actually very small objects, right? Unfortunately, I guess we've never observed any. So, all right. So, what is the link between cosmic strings and time travel then? Why are we talking about cosmic strings in your time travel presentation?
So when you take a cosmic strings, you have a big gravitational pull, and when you take two cosmic strings and you loop around them, you can go into the gravitational pull of the cosmic strings, and because their gravitational pull is very big, you can go faster than light.
Okay.
And when you go faster than light, of course, you go back in time, and that's why we talked about it.
Right. So again, it's all a question of gravitation. Okay. Maybe we might come back to cosmic strings later because there were quite a few questions around it. It was one of those things that really, I think, tickled the fancy of most of your classmates. What else did you guys talk about? So, because the main topic remains time travel. So the first idea, just so it was clear, you're saying that cosmic strings, if they do exist, would be something that potentially could permit us to go back in time by virtue of the fact that they have such a strong gravitational field that if we get stuck in orbit around it, we would be going faster than light potentially. Okay, Rose.
And I presented another way to travel through times, which is wormholes. So it's basically an association between a black hole and a white hole. So I can explain a bit what is a black hole. But
I think this is good also because we've had at least two other groups who've talked about wormholes. I think, Antoine, you guys spent a good 20-30 minutes trying to explain the geometry and the mathematics of it. And also we had the gravitational group last week who mentioned wormholes a little bit. So go ahead, Rose.
So a black hole is an object whose entire mass is concentrated in one point in particular, which can curve the space-time around it and create a sort of a hole.
Do you remember what's the name of that one point where all the mass is concentrated?
An horizon.
So that's the space around it where if we go past... So you can remember, Antoine, what was the event horizon of a black hole?
Eventually there's a certain distance from the point where all the mass is concentrated, where the gravitational pull is so high that even light can't escape.
Right, in order to escape we need a speed higher than that of light.
Exactly.
And what is the name of the point where all the mass of a black hole is concentrated?
And so I don't have it either.
It's a singularity.
Yes, there we go. It's called a singularity, and it's a problem for us in physics because at the singularity we don't have laws of physics that can actually describe what goes on, so we can't say what happens if and when we get there. Black holes have been observed, or are they like cosmic strings, Rose? We know?
They have been observed.
Right, that we've observed indirectly and almost directly because we can't actually see them because there's no light escaping from them by definition, but we've seen photos of the stuff around it, and we've detected gravitational waves from collisions of black holes a few years ago. Big deal. All right, so go on with the black holes and time travel.
Yes, and a white hole is the opposite of a black hole. It will reject everything instead of absorb everything. And so the black hole and the white hole are linked together by a sort of a tube that we could cross to travel through times or through different places in the universe or through different universes. And that is called a wormhole.
Right. How does that allow us to travel in time? Because what you're describing to me sounds like it allows us to travel in space. It allows us to go from one place to another, which is really far away, by kind of making a shortcut. How is that allowing us to travel in time?
It could relate, link together two different moments in the universe, but I can't really explain it.
Zainab, do you want to give it a shot? Because it's linked with the idea of the speed of light, right?
But it depends of how the wormholes is also made.
Explain a bit for us. What do you mean by that?
I think that if I'm not sure, I would say it's very a very shaky explanation, but
it's okay. We like shaky things here.
So, if for example you take, I think it's more related to the geometry of space than that of the speed of light.
Well,
I would say.
Antoine, do you have an idea how a wormhole, which is sort of a shortcut through space, can allow us to travel in time?
I would guess that if we speak about like the theory of general relativity, that says that nothing can go faster than light. But the fact is that if we use kind of shortcuts through space, we can go faster than light from a certain point to another. So that would also mean kind of shortcutting time in a way.
Or going back in time in a way. So the idea being that if you have to go from A to B by the long way, you get there in 1,000 years. But if you can go through a shortcut, you get there in a day. It's kind of like you've come back in time 1,000 years because you've reached there much quicker than light would, right? Which has to take the long path, right? So in that sense, the idea of time travel can be integrated into this idea of wormholes because we are, in a sense, going faster than light. And the distinction we make is, so locally we're not going faster than light because we can't do that, but globally we're going faster than light from these 2 points. Okay, so we talked about cosmic strings, we talked about wormholes as 2 ways of potentially having time travel. What other solutions did you guys find in your research?
It was something called closed time-like curve.
Right, CTCs for short.
CTCs. And so it's depend of the geometry of space. You wouldn't like actually go faster than light, but you would just a universe where everything would go back to its beginning. So for example, I live my life now, and if I am on a closed time-like curve, I could go back when, for example, I am 70 years old. I could go back to this day when I'm doing my podcast, and it's just a natural geometrical structure in space and
time.
In space and time,
right?
And it was made thanks to the theory of Einstein, the
general relativity, which basically tells us how the way mass and energy is distributed can change the geometry of space and time. And you're saying that, so one of the solutions to the geometry of space and time is one where you have loops which are closed, which means that they come back to the starting point. Again, I guess, so here we're not cheating because we're not locally going faster than the speed of light at any moment, but it's just the natural geometry of space is that. Yes, Antoine?
By solution, do you mean that it actually fits in the Einstein's equations?
Right,
geometry?
right.
Okay.
So we can have solutions to Einstein's equations, which are mathematically correct. The question is, do they have physical meaning, right?
Yeah.
So when we say do they have physical meaning, which would be the next question I think that comes up is, so closed time-like curves, CTCs, are theoretical solutions. Have we observed CTCs? Or have we even thought about how we could test for CTCs?
So we haven't observed CTCs, and it's just a theory. But I don't think we can think of a way to observe them. Or maybe
I guess the easiest way to observe whether there are CTCs is if we see people from the future, right?
Yeah.
Right? Okay. Did you find other interesting things with the CTCs? Because that was one of those interesting topics that a few students had questions. Okay. What other topics, what other solutions do you guys find to time travel, if any?
That's it.
That's it. How about we talk a little bit about the problems with time travel? What do you guys think? Like paradoxes in time. So what do we mean when we talk about a time travel paradox?
It's, for example, the most known one. Yeah, it's called the grandpa's paradox.
Right, grandfather's paradox.
Yeah.
Okay.
And for example, if you go back in the past, before you were born, and you kill your grandfather, you won't be able to be born later, and you won't be able to go back to kill your grandfather. So this is what we call a paradox. It means that something non-logical happens.
Right.
When you go back in time, and which make it impossible.
Right.
And so there was a few solutions. If you want me to talk about
Sure.
them.
Let's hear the solutions. You're going to solve time travel for us. I'm always up for that.
We can't go back to the past or the future now, but maybe later.
Let's see. So let's share some of your secrets with us.
So maybe when we create a time machine, we can I create a time machine today. I put it here and I live my life like normal. I go back, and for example, when I am 70 years old, I use my remote.
You clearly have a fear of 70 years old, because the second time you want to come back when you reach 70 years old, no? All right.
Okay, it's because I will
Let's
be
say 75. You're older now.
75 years old. So I will take, for example, my remote, and I will go back into my time machine, and I will come back to this point in time. And I could, for example, create a new, different life for myself. I could live different things and do...
Okay, so how does that not create a paradox? Because you're saying that's a sort of a solution, and we talked about the grandfather paradox before. How does that not become a paradox?
It's because... I didn't change my past, and the things that I changed, they are they will create a universe, a meta. I don't know. I'm sure you know about the metaverse.
The multiverse.
So, the multiverse.
Yes, metaverse is something else. Yeah.
And so I will create this path that I took in my first life. It will be a universe, and the other one that I will create, it will be a second universe, and I will not kill myself, for example, where I wouldn't exist, or I wouldn't go back before my time machine was created, and so it doesn't create any
So
paradox.
that's interesting. So one of the things that this problem solves is that you can never go back further behind in time than the moment where you activated your machine. So the question that always you can ask when people say time travel is possible is okay, if time travel is possible, how come there's nobody from the future that we see? In which case, your answer would be, well, time travel becomes possible from the moment where the time machine is created. We haven't created a time machine. So if suddenly tomorrow you are able to create a time machine, from tomorrow forward, we'll have lots of time travels, right? So that's one way of looking at it. The other way of looking at it, which I guess kind of goes back, so I'll ask it in the form of a question. Imagine you have this time machine, okay? And you reach 75 years old and you decide, okay, I want to come back to the day I started my time machine. When you come back to that time, are you your 75-year-old version, or are you the version of yourself when you created the machine and started it? Because that is a real question, I think, in a way.
Yeah, I think it would be more of the mindset, and the mind that will be 75 years old, and my body would still be...
Oh, so you just want the best of both worlds. So I'll be young, but I'll have the wisdom of a 75-year-old. Yeah, I think you're very optimistic with when it comes to time travel. Because if you want, in a way, the solution to time travel, which would be, I guess, not in contradiction with the grandfather paradox, is that you do come back in time, and you do whatever you do, but when you're there in that time, you are your older self. So there's a continuity. So there's not two versions of yourself running around. There's still only one version of you present at that time. And each version is a different one. One is the younger one is the older one. In that case, I suppose there's an issue that is solved. What other solutions did you guys find to time travel? How did you guys manage to time travel? No, you didn't find any solutions? No? Antoine, do you have any ideas?
The solution to time travel? No, not really.
No solutions.
Go faster than light.
So it's interesting because there's different ways of also thinking about the grandfather paradox. So one solution is to say, well, for example, I can say, yeah, I can learn to speak Finnish before the end of the school year. But realistically, I'm not going to be able to learn to speak Finnish before the end. So the idea would be that even if you come back in time and you try to kill your grandparent, somehow you don't manage it. Because if you had managed it, then you wouldn't exist. And if you didn't exist, you wouldn't be there to do it. So in a way, it's like the universe protects itself from paradoxes. Another way of looking at the grandfather paradox, which I think I find more interesting, is let's imagine Rose, because she's bored during the holiday, she decides to go to the Louvre and she steals La Joconde, so the Mona Lisa. And then she goes back in time and finds Leonardo da Vinci before he'd painted it, and he shows the painting to Da Vinci, and Da Vinci copies it. And then that becomes the original version of the painting, which we find in the Louvre, that she's going to steal and go back in time. And the subtlety there is that, so it's not a question of killing your grandfather, but then the question becomes, okay, so who had the first idea to paint the Mona Lisa? If the person who painted it copied the version that was taken from the future, right? So there are different ways of formulating these paradoxes. So Antoine, how about we go to some of the questions from the classmates? What do you think?
Yeah.
Is there any one that really struck you as interesting, bizarre, or...
A bizarre one would be the...
Yes, I think I know which one you're going to say, yes.
The legal one.
Right, so Lisa asked, is time travel legal? And there is a very definite answer to that. Is it legal?
I think the question is not very asked because we can do it, so...
So if it's not
There is no
illegal,
law.
then in a way it's legal, right? So time travel all you want, you're not going to go to jail for it. I thought that was a pretty funny question there. But let's, maybe another question, Antoine?
A question about the black holes, asked by Luan, that says, why does the black hole have to be in rotation on itself? Which I believe is more physics
Right.
than math.
So just as a quick reminder, we have different types of black holes because each black hole is a solution to Einstein's equations. So there's just a normal spherical one, then there's a spherical one that's spinning, then there's a spherical one that's spinning that has electric charge. Each of these are different solutions to the equation. So you guys mentioned that the spinning black hole is the one that would allow maybe time travel?
Yes, but it's in the geometry of the wormhole. Like it's not the black hole itself. It's
so the
in
black hole
whole,
half
yeah.
of the wormhole. Why spinning?
Because to be stabilized in time, to go against the forces generated by its geometry, the forces of the space-time, we have to put a sphere of for a sort of ring of full of negative energy, and the rotation creates a sort of negative energy.
Right, this negative energy. I think one of the other reasons for the spinning black hole is because if it's not a spinning black hole, we've found that we can't actually go towards it. I'm super simplifying the thing, but with a spinning black hole, you can actually go towards it without actually falling in necessarily in a irreversible way. So I think that might be part of it. Any other questions you found interesting? Because we have about 4 or 5
that
minutes
might
left.
be linked about how we use black holes, because you said that it wouldn't be necessarily the black hole itself that had to be spinning, but it would be about the geometry of the wormhole.
Yes.
And one of the solutions that we use for wormhole is a model called the Morris thorn. And there's a question about Pierre, which is what are the conditions for a Morris thorn wormhole too?
Yeah, so it's the same conditions, but there are a lot of geometric wormhole and different shape of wormholes, and one of them is the Morris thorn wormhole, and it's the one that could work better, but it has also to be stabilized in time by negative energy, but in the general relativity theory, a huge quantity of negative energy is not correct, so we have to work in others theories like the quantum field theory, but
Right, so basically you're saying that Einstein's relativity is not equipped to answer all the questions that we're asking because it doesn't consider the quantum level, and we don't have a quantum theory of gravity. Just as a reminder, all the stuff that you guys have researched is stuff you've researched which is way above your school level, so it's not easy to answer these questions because they're very technical. So let's make a little short list. You said cosmic strings is one potential solution, but we've not observed it. You said that black holes are one potential solution, which we have observed. Wormholes, maybe. Have we observed wormholes?
No.
Okay. CTCs was one potential solution. Have we observed CTCs? No. Basically, time travel doesn't seem like it's a very easy thing to do, right? Okay. Well, in a way, we can say that we're always time traveling because we're always traveling in time forward. So when we talk about time travel, it's like the idea of traveling where we want or when we want in time, forwards or backwards. That's the problem, right? In space, we can go forwards or backwards, left or right. In time, we can move, but we're much more limited. So that's basically the essence of what time travel is. Okay. Well, before the bell rings, what did you guys find interesting that was particularly, surprising that you didn't know, that you found remarkable in your researches? Zainab? Rose, you want to start?
Yeah, I think I saw somewhere that the idea to time travel comes from the sword in the stone with Merlin.
The old English myth.
Yes, because I think Merlin had the power to go back in time and to go in the future. So Celtic people believed it was possible and started to search for ways to time travel.
So basically you're saying that we've been wanting to time travel for a long, long time.
Yes.
As long as there's been human regret, I think we've wanted to travel in time, right? Zainab, what about you?
It was about everything about the paradoxes and how cosmic strings are made. It was very interesting to read about and to watch videos.
Okay. Did you find it was particularly difficult to find stuff which was at your level when it comes to time travel?
Yeah, it depends. Cosmic strings, they were really hard to understand.
Yeah, I can understand that.
And I had to watch a lot of videos to kind of understand how it works, basically. But yeah, it's kind of...
But you managed to do a pretty decent job. Antoine, what did you find interesting in the topic? Because I think you guys, your topic was quite closely related in some ways.
Yeah, I believe that the fact that what we've done is really about the geometry of space and space in itself, not especially about time and the time fabric. And I believe that the fact that we're only limited, as you said, in going forward and in a certain time and at certain speeds, kind of rings me about what we've done with the Newton's equations.
Right.
And kind of rings the idea of there's some forces that could make us go in a way that would break this kind of linear speed in time.
This sort of limitation in terms of how we can move around. All right. Well, the bell has rung, so I think we need to bring this to an end. So it would have been fun to discuss more, especially the paradoxes, because there's lots of interesting stories in there, but we'll have to cut it short this time. So thank you for your presentation, both of you guys. You did a really interesting job. It's not an easy topic, but we enjoyed it very much. And thank you to Antoine, my co-host for this week. We'll be back next week with another episode. This time, I think we're going to be talking about exoplanets and 2 new students. So thank you very much and have a nice day.